We're going to continue our work with slope fields. We're going to review here really quickly. This says draw the slope field at the 9 points closest to the origin for this differential equation. dy dx equals x times y squared. So those 9 points closest to the origin would be these 9 points right here. So those are integer points, all of them. We'll start with this one, the point -1, 1. When x is -1 and y is -1, the slope is -1. So there's that piece. The next point is 0, -1. Well, we realize quickly anytime x is 0, the slope's going to be 0. We could also realize using the point -1, 0, that anytime y is 0, the slope's going to be 0. So the work for this was shortened quite a bit just by realizing there are many of the points that we can get when either x or y equals 0. Let's look at the point 1, -1. The slope for that point winds up being a +1. Let's look at the point -1, +1. There we have a slope of -1. And the point 1, 1 gives us a slope of +1. So there we have it. A quick review of how we are going to draw a slope field if we are asked. Remember, they will tell us or highlight the points that they want us to use. Here are what a lot of your multiple choice slope field questions are going to look like. We've already seen questions like this where we're given a generated slope field and we're asked to either find the function y or f of x that the slope field represents, or in this case we're asked to find the differential equation that this slope field represents. So it's a little bit different when we're looking for the differential equation. It's very nice to pick integer points to try and see what might be going on your function. It appears that those are -1 and 1 on both the x and y axes, so we can get an idea if we pick integer points what should be going on. This one jumps out at me. When we have 1 and -1, specifically x equal 1, y equal -1, we should get a slope of 0. Let's look at these individually. On A, when x is 1, there is no y in this differential equation. That's definitely not going to equal 0. When x is 1, that will not equal 0. This is the case where x is 1 and y is -1. We could get a 0, so that one's still in the running. For D, we're definitely not going to get 0. And for E, that one is undefined there. We shouldn't have a slope there at all. So by process of elimination fairly quickly, we can determine that that indeed is going to be where the slope is 0. As a matter of fact, we could verify that and say that any time the x and y coordinates have the same magnitude but a different sign, their sum is going to give us 0. So that verifies for sure that C is the correct differential equation for this slope field. Let's look at one more example where we have a generated slope field and we're asked to find the differential equation that matches this slope field. This one is a little more complicated because of the form of all of the differential equations. All of the differential equations are quotients with x in the numerator and y in the denominator. It should make sense to us that everywhere that y equals 0, we should have a vertical tangent line, and it appears that that is what's going on. So that's really not going to help us. It should be true that everywhere that x equals 0 and y is a well-defined value, we should have a horizontal tangent line. So again, that's not going to help us. We're going to have to look let's see here, 1, 2, 3, 4, 5, 6. So every 2 of those is a tick mark. Here is x equal 1 and x equal 2. We could come away from that. Here's -1 and -2. Let's look at what we might get when x is a positive value and y is a negative value. For instance, just for trial and error, let's try that. When x is 2, this one is negative. That one is out. When x is 2, well, as a matter of fact, this one is always positive, so it's still in the running. This one would be negative when x is 2 and y is -2. We're looking for a positive slope at the point 2, -2. This one as well, d, would be a negative value. That one's out. But e would be a positive value. Not always positive, but sometimes positive. So that kind of sort of lets the cat out of the bag here. These slopes are always positive. If I'm drawing a slope field for this differential equation, every single slope in that slope field should be positive. And I can clearly see that it's not that way. So again, by process of elimination, really, I determine that E is the correct differential equation for this generated slope field. Consider the differential equation dy dx equals x plus 1 over y. I'll write that a little bit bigger so you can for sure see it. Here is our differential equation. A says, on the axes provided, sketch a slope field for the given differential equation at the 12 points indicated. And for x between -1 and 1, sketch the solution curve that passes through the point 0, -1. So we have 12 points highlighted here, 6 above the x-axis and 6 below. Let's plug those integer values into our differential equation and see what we get. When x is -1, y is -2 at that point. -1 plus 1 is 0 over -2. The slope through this point is 0. As a matter of fact, any time that x has a value of -1, your slope is going to be 0. So I can take care of 4 of those immediately. When x is 0, as in the case on these points, anytime x is 0, the slope is really determined by what the y value is. So on the point 0, -2, the slope is -1/2. So -1/2 would look like that. When y is -1, the slope is -1. Again, they don't ask us what's happening when y is 0. When y is +1, the slope is +1. And when y is +2, the slope is +1/2. Let's jump back down to the point 1, -2. It might help us for the values where x equals 1 to write down, this is how we're going to determine what the slopes are. So at the point 1, -2, we have 2 over -2. That's a slope of -1. At the point 1, -1, we have a slope of -2. At the point 1, 1, we have a slope of +2. And when y equals 2, we have a slope of +1. So again, not terribly time-consuming, especially if we look for trends. Now let's work the rest of part A. That's just the first part, draw the slope field. And it says, for x between -1 and 1, sketch the solution curve that passes through the point 0, -1. Here is 0, -1. So we want to follow those little tangent lines. We're headed this way. It will help us to realize that anytime y equals 0, we're going to have vertical tangent lines. So I recognize that I'm going to come off of this slope, and this one's going to turn me around and head me back in that direction. So there is a solution curve that passes through the point 0, -1. And there is all of my work for part A. Let's move on and talk about part B. I'm going to move this down a little bit since I've rewritten the differential equation. While the slope field in part A is drawn at only 12 points, it is defined at every point in the xy plane for which y is not equal to 0. Describe all points in the xy plane for where y is not equal to 0, for which dy dx equals -1. We know dy dx is x plus 1 over y, and they want us to describe all the points in the plane where this is a true statement. Well, let's just play around with this ratio a little bit. I'm going to multiply both sides by y. That tells me that x plus 1 equals -y. It says describe all points in the plane. Well, we could say that all points have the relationship that 1 plus the x coordinate must be the opposite of the point's y coordinate. There's a description. We could manipulate it more with algebra and write another description, but that's close enough for me. I'm perfectly fine with that. Now let's move on to C.